Okay, this first problem is a circular permutation problem. It's saying we have 6 people around a table, and here are the people, A, B, C, D, E, F. Those are 6 people. How many arrangements can we have? And so what happens here is we have A, B, C, D, E, and F. And if we try and lock in the positions of the table, it doesn't really work for us because unfortunately, since it's a circle, I could rotate it, okay? And people are in different positions now. If we called the top the 12 o'clock position, just like a clock, right? A has gone from 12 o'clock here, and now it's at, roughly 3. And F is at our 12 o'clock. However, this is still the same arrangement, okay? Again, we can keep rotating these circles, okay? D is now at the 12 o'clock, and A is at the 6 o'clock. However, this is still the same arrangement. Okay, so what we need to do is we need to think of a strategy on how to solve these circle problems. So let's draw a circle, okay, and let's make 6 spots. Let's go 1, 2, 3, 4, 5, 6. 6 positions. The way that we are going to solve this is what we do. The first thing we do is we lock in a position. So let's lock in this 12 o'clock position and say that A is going to go here, okay? We are locking it in by saying A has to go here, okay? How many ways can A go there? Well, there's only one way that A can go there. Now that we have one position fixed, okay, and we'll call this the fixed position, we can go through just like position. We can go through just like before, just like we had a lineup, okay? So what we'll do here is we'll say, how many more choices do I have for here? I have 5, 4, 3, 2, 1. So how many arrangements can I have? Well, there's 1 times 5 times 4 times 3 times 2 times 1, okay? In general, what we do for any circular arrangement, let's say I had a new problem where I have only 4 people to sit at a table, okay? What I'm going to do is I'm going to lock in one position, so that'll just be a 1, okay? And then I just go through my normal permutation logic, okay? So how many more choices do I have? 3, 2 for the bottom, and then 1 for our spot on the right. In general, we're going to take the number of people, okay? And we're going to have an answer of n minus 1 factorial, okay? This only is for circular arrangements, and this deals with the fact that we have to fix a position. Okay, so back to our original one. If we had 6 people around a table, and we have this as our answer, okay, 1 times 5 times 4 times 3. Really, we could have said, well, n equals 6, so there must be n minus 1 arrangements, or 5 factorial, which this is what this equals, okay? So again, n minus 1 factorial arrangements for circular permutations. Okay, this is dealing with number 35 from page 661. It's essentially saying that there's a light bulb company, and what they're doing is they're testing 5 bulbs out of 100 to see if they can find any defective bulbs, okay? What defective bulb means is that they're just not going to work when you plug them in. So the question then becomes is how many different ways could a bulb sample be taken? The key word here is different. This is telling us that the order does not matter, okay? Order does not matter. Okay, if the order does not matter, it means we have the equation of 100 choose 5, which we're just going to shove that right into our calculator. So we're going to do 100 math probability choose, and we're going to choose 5 of them. This is going to give us a nice big number of there's 75. Ooh, no, even bigger. 8, 7, 5, 2, 0, 1, 2, 3, 1, 2, 3. So 75,287,100,520 ways, okay, different ways, in fact, that we can find, or that we can take a sample of 5 bulbs. Okay, part B of the question kind of changes things up. So it says, to check the quality of the control, the supervisor puts in 2 defective bulbs and 98 good ones. Find the probability of at least, okay, and this word here, at least, is an indicator of how we're going to think of this, okay, of at least 1 defective bulb. So out of this 100 now, there are 2 losers and 98 winners. We can think of it that way. Or we can think of it as reverse, if we want to think of the defective ones as winners and the 98 as losers. So define the probability of at least. It's actually going to be easier to say 1 minus the probability of no defects. Or in this case, the probability of no losers. Scratch that. Just no defects, okay? So the probability of at least 1 defect is equal to the probability of 1 minus the probability of no defects. The probability of no defects is that there are 98 of these no defected bulbs, and we want to choose how many? Well, we're still testing 5, so we're going to choose 5. And we need to do this over the entire sample space, which is going to be there's 100 bulbs in total. Choose 5 still. Okay. So this will lead us towards our answer. So let's see. We're going to do 98 math probability. Choose 5 of them. Gives us this huge number. Okay. And I'm just going to hit divide by. I'll put some parentheses around 100. Math, probability, choose 5, which is going to give us 1 minus, try and move this up here, 1 minus this number, which is 0.0902. So 1 minus 0.902020, repeating. This gives us a grand total of 0.09798, or that there's the chance that 97.98%, there's a 9.798% chance that we'll get at least one of the defective bulbs. Okay, again, at least is a key indicator of that we want to do 1 minus no defects. Okay, so if it says at least 1, we want to do 1 minus the probability of none. Okay, this is problem 31. If you feel comfortable on this, you can just go ahead and end your video watching now. But I feel it's a good idea that you watch me go through this. Okay, 31 says that there are 15 people. 6 of them are left-handed, 9 of them are right-handed, and we're going to select 7 at a time. We want to find the probability that when we select these 7, we'll get 3 lefties and 4 righties. So how we're going to do this is we are going to say, well, how many lefties are there? There's 6. So we'll say 6 choose, and how many do we want to choose? Well, we want to choose 3 of them. Okay, times we have 4, or we want 4 righties. So how many can we choose from? There's 9. Choose 4. Okay, and then we need to divide by our entire sample space. So what's going on any given experiment? Let's see, we have 15 people to choose from, and we're choosing 7 of them. Okay, this is going to give us a probability and give us the correct answer. Notice here that everything on the left side of the C is adding up to 15. So 9 plus 6 is 15, the entire sample space. And then 4 and 3 is equal to 7. When we have simple and probabilities like this, this is always going to be the case. If you throw in an or in here, things get a little messier. So this is the setup. I'll leave you to completing the problem. Part B asks for the probability that everyone's going to be right-handed. This leaves us, let's see, let's go through it. So there's 9 righties to choose from. How many do we want to choose? Well, we want to select all 7 to be right-handed. But to stick with our rule, okay, we still need to have everything on the left side of the C equal the entire sample space. So over here, how many lefties are there? Well, there's 6. And how many are we choosing if we've already chosen 7 right-handed people? We're just going to choose 0 of them. Okay, 6 choose 0 is going to be 0. Okay. We still need to divide by the sample space, which is going to be, there's 15 people we are choosing from. We are choosing 7 of them. Okay, again, this is going to be the setup for B. This is a 0. And I will leave this to the watcher. Part C, we're doing the same idea, but we're doing all left-handed people. I'm just going to go real quick on this. How many lefties do we have to choose from? There are 6. How many do we have to choose? We want to choose, well, we want to choose 7 of them. Can we choose 7 lefties? Oh, this problem just got more interesting than I thought. So can we choose any situation in which we'll have everyone being lefties? Well, the answer is no, because guess what? There aren't 7 lefties. So are not 7 lefties. Okay, so this actually becomes 0. That was a much more interesting question than I thought when I initially started. See if you guys can make sense of it. Okay, part D says that Harry and Pegleg, 2 different people, and it was given that these are lefties. Okay, we want to guarantee that these guys are chosen. So out of Harry and Pegleg, how many people are there? There's 2. How many do we want to choose? Well, we want to choose 2 of them. Okay, and then we don't really care what the rest of the people are. So how many people altogether do we still have to choose from? We have 13, and we're going to choose, we've already selected 2, we're going to choose 5 more. Okay, we'll divide this by our entire sample space. So this is going to be 15, choose 7. Notice that our rule still works. We have 2 plus 13 is equal to 15. And we have that 2 plus 5 is equal to 7. Once again, I will leave you guys to do the calculation at home.